Now here's a very nice concept called numerical approximation, Euler's method. So when we have very hard differential equations or pretty much different kinds of curves we are unable to solve for some reason or approximate, we use Euler's method to get really nice approximations, and these approximations help us understand curves like this, sometimes differential equations we're unable to solve, and get a really clean result. Okay, Euler has generated a very nice method to derive these curves. So for example, I have this curve, this blue curve, okay? And what Euler does is he gets one distance, okay, delta x, okay, our step size. And let's say our step size is 1 for the sake of this argument. And at every one he gets another slope. Okay, so we have the red slope first, and then the yellow slope, and then the purple slope, and then the green, and then the red blue. And at every same step size we get another slope corresponding to the point of this graph. And using all of these slopes together, we are able to see a very nice visual picture. Like for example, if I make it more visual to you guys, you will get stuff like this, okay? And you can actually tell that this curve looks like something like this. These are different line segments that are attached to each other, but they do kind of represent our original curve here. And what Euler is actually doing is pretty much just attaching these slopes together to approximate a curve looking like this. So what is the formula for Euler's method? So when we want to use Euler's method, we have this very nice formula. dy dx, our slope, is equal to f x and y. As we covered previously in direction fields, we have a slope field. Okay, we know what our slope is in a function of x and y. We are given an initial condition. You need an initial condition to build Euler's method. And we are given a step size. You can create your own step size. And the smaller step sizes you have, the smaller it gets, the more accurate picture you have. So if h approaches to 0, our accuracy, our error approaches to 0 as well. Because basically this is the only part that's causing error, because as we have larger and larger, for example, consider this first point, and let's say our h was something like 10, right? And our slope are so different, right? The first slope is so steeper than the second slope. So the smaller step size we have, the more accuracy we get. So we can use computers to help us generate really close approximations for these methods. Also quite similar to Taylor series in a way. And basically our function is going to be our next step, yn plus 1, is going to be, this is a point on the curve, okay? This point will be the first point plus the slope multiplied with the side, the step length, okay? Delta x. Delta x also means h in this case. So this equation is a very smart way to build up this approximation. So our second point will be equal to the first point plus the step size multiplied with the slope of this point. Very smooth. And that's pretty much all we have to know. Usually what you will be asked is to solve a problem given you have to quite know this problem, this formula, if you may. You need to know the formula and you understand it. And once you understand and know it, you can approximate many steps using this formula. Now let's work on this very nice example problem. Dy over dx equals to y, and y0 initial condition is given to be 1, and our step size is 0.5, and we are asked to compute 3 steps. Before we start computing using Euler's method, I want to show you the first actual equation, the actual solution to this differential equation. We would use separable. Right? dy over y would be equal to dx. I would just switch the dx and y. Then we would integrate both sides. On the left-hand side, I would get ln of y plus c. Or you can add the plus c on the right-hand side, which would be better, and x plus c. And we would take the exponent, and y would be equal to e to the x times c, and our initial condition is given to be y0 equals to 1, so y1 would be equal to c, so that would mean y equals to e to the x. Now that we have found y, we can plug x equals to 3, and our solution will be e to the 3, which is around something in fourths, okay, 4.4-ish, okay? Now that we found this, let's now use Euler's approximation to solve this equation. Well, it is important to note our h value is actually a quite large number because these functions such as e to the x grow so much faster than other functions. So since it's an exponential function, I do expect to see a little bit of a big difference because of the largeness of h. If we had like a 0.1 or a 0.01, we would definitely be somewhere in really close to this range. However, I'm expecting a little bit of a difference here. So let's start building our first three steps. y1 equals to y0. Okay, y0 is what? 1. Okay, plus f of our derivative. Okay, at y1, okay, what is our derivative when y equals to 0? I'm sorry. Our derivative is actually 1 because our y equals to 1, so our derivative is actually equal to 1 too. So 1 times 0.5. Okay, so y1 equals to 1.5. Now let's build y2. y2 is going to be 1.5, which is y1, plus, and still at y1, our derivative, our slope is 1.5 again. So we will have 1.5, or in other words, 3 over 2, and our slope is 1 over 2. So our slope is going to be 3.3 over 4, which is 0.75 plus 1.5, and this will be 2.25 equals to y2. And our third and last solution will be y3 equals to y2, which is 2.25, plus our slope at that point, and it's still 2.25, and multiplied with 1 over 2. Okay, so how can we express 2.25? So 1 over 4 plus 2 will be that. So it's actually 9 over 4. This is 9 over 4 multiplied with 1 over 2. So our actually addition is going to be 9 over 4 plus 9 over 8, which is going to be 1827 over 8 equals to our third step, which we were looking for. So let's divide 27 by 8, and we will have 3, 24, minus 0, 3, and somewhere, what is this, 4? 3, 24, I believe, yeah, 0, 6, and something like this. Okay, so we will have not 5, but 7. Yeah, 7. Yeah, something like 3.37. Okay, so our approximation provided us something like this. However, because this was an exponential function, we do get a little bit of an off result, which is completely okay as long as you used Euler's method. You should be in good shape. Most other times, if we don't have an exponential function like this, it doesn't really matter because the expansion rate will be different. However, in this case, we did have an exponential function, so it is important to have smaller step sizes if you want to get more accurate approximations. And you can use computers. There are really nice tools on the internet to get really nice approximations using Euler's method.